let's go through the build method. We're going to do just some preliminaries, so we're going to kind of build this up like we did the central limit theorem. Go through some prelims. Next time I'm going to give you a rough proof, and then I'm going to butter it up and make it a more complete proof, kind of like what we did last time. So, let's say like the master's level proof versus the PhD one. Does anybody know what the delta method does? Anybody ever heard of it before? They didn't teach it in undergrad stuff. If you're a stat major, you may have seen it. So back in the 1960s, I imagine this was pretty cool stuff. I did reach out to a couple of my engineering friends, and I was asking them about Taylor expansions. And they said, we use them all the time. You don't know what you're talking about. It's not just like a proving thing. And one of my friends kind of very clearly stated it for me. It said, we don't care if we're approximate. All we want is the ballpark. So we let you guys fix up all the theory and get even closer. So our assumption is that all your assumptions are wrong anyway. so we do these sort of things. So, don't just listen to me. So talk to other people, see what people in different fields do. And I tend to think the things that people use in different fields tells you a lot about what they do. So, and why they do it. So saying that, if you're paying attention to all kinds of different fields and you see something new come up, maybe you can introduce it to your field and take it a step further. Okay. The delta method. I'm going to just do the preliminaries today. I probably should follow Brendan's advice and tell you what we're doing and why we're doing it before I just start doing a bunch of stuff on board and then put it all together at the end. So I have this fantasy that you guys read it in advance or at least skim the thing and you know what it is. Am I an idiot? At least for that reason. Yeah? All right, okay. That's okay. It's good to know. I'm starting to catch on after 16 years of this. Okay, so the delta method applies to transformations of variables. So the goal is to transform random variables, and sometimes that's hard to do. So the goal, transform random variables and sometimes these are hard. I would say it's not difficult if you're able to sample from a function that you can transform directly. So computationally, transformations are just really easy to do. If you're able to sample from the distribution directly, and then you can apply the transformation to those samples. So I tend to think it's not really a difficult problem, but I guess it depends on where you are, so what you're doing, what your resources are. And I should say sometimes the delta method can be useful. And I will say this, you probably need to build a simulator anyway to see if the delta method is approximating well. So this is an asymptotic method. Does anybody know what I mean when I say it's an asymptotic method?
We're assuming that it's going to treat it like it's going to infinity.
Yeah, so it says we do the... Sorry about that. Yeah, that's kind of irritating. Let me see if I can do something about that. Off. Okay. One more time.
We're in this asymptotic, yes, it's on.
It's like a little hammer.
We're treating it like our sample size n is going to infinity.
Yeah, it's a statement that says as n goes to infinity, the method works. What do you think of that? On its own. It is better. You know, any coherent, reasonable thing better do the right thing if you had the entire, everything. As n went to infinity, you got to see the entire population effectively. So I would think that that's true about anything. I tend to like methods that work conditionally, or conditional on the data set that you have, and you can prove properties about that. So I do like limiting approaches and thinking about things in the limit. You know, I usually use that as an argument when you stress this idea and take it to the extreme and see if there's a fundamental breakdown. So I think asymptotic methods on their own, if you're just enamored by them, you're probably a mathematician. Say that this can work sometimes. And so I'm going to give you a problem that's going to purposefully mess up the delta method. So I'll kind of talk you through that a little bit and show you a problem where the delta method probably works okay. So, but what I'm saying is that you need to check. And the only way I really know how to check is you make your assumptions about your random variables and do a simulation study and see how well the method works. I'm going to walk you through that. So there will be a simulation study concerning the delta method, and you'll do this checking. And I think you should always check. So anyway, this doesn't work for any transformation of random variables. This works for random, normal, limiting normal random variables. So transformations like G of something, I'll just call it X, N, I'll just call this Xn. Right here. We might be interested, if we know what the distribution of that is, we want to consider some function of that random variable, and it's going to change its form. Delta method is specific about this being a normal sequence of random variables. I don't mean that they're absolutely normal, I mean that they limit to normals. So an example would be x bar. So usually you apply this to something like a mean. So limits. And we're going to show that under the delta method approach, that thing also is asymptotically normal. So let me just write down the statement of the delta method, and we're going to take, an hour and a half to prove it. So delta method statement. That didn't help at all, did it? I've asked many times, why don't we get rid of these things? So apparently it just costs too much money and there's not a line item for the university, so we have radiators still. So anyway, and it kind of, my experience with them is they run really well when it's hot outside. They do all this clunky stuff when it's cold. Delta method statement. Let Yn, this is I think the notation that they use in the book, be a sequence of random variables such that square root n, Yn, whatever that thing is, minus its mean, I'll call that theta. So this is going to be the expectation of Yn. Converges to a normal 0 sigma squared. So I've basically just written down the same statement that we wrote down in the central limit theorem before, and I just collected my sigma squared over here, where before the sigma was over on the left-hand side. So, but this is just a statement that says it's asymptotically normal. Then, for some smooth function, So this has to be smooth also. So there's going to be a Taylor expansion in here. So G smooth. It does not need to be quite as smooth as it needed to be for that proof of the central limit theorem. We didn't need all those smoothness conditions. It just made the proof a lot easier for the CLT. But we did need to assume all of the derivatives existed. So we couldn't apply that proof to like a T distribution or something like that that doesn't have all of its moments. All we really need for the delta method is the first derivative to exist. There is something called the second order delta method, and maybe you'll glance at the book and see what the second order delta method does. So if you don't look, I'll tell you. Then square root n g yn, transformation of the yn minus g theta is going to converge to a normal 0. Does anybody know what the variance is here? I'll put in the easy part. It has something to do with the original variance. Oh, and this is the variance of the original yi's, not of the yn. I've collected the n over here. So if you're thinking about this thing is x bar right there, then the xi's variances are the things that I put over on the right hand side. Does anybody know what this term is right here? G prime. What is it evaluated at? Theta. Is that right? Squared. Very good. So this is the part I always forget myself. Squared. So you need that square there. It doesn't seem like it would be hard to forget that square, but for some reason, every time I do this, I always forget to square it. I know that it's supposed to be squared. When I do the calculation, I'm working through the derivative. I finally get the derivative. I plug it into the thing, and I forget to square it. So when I forget to square this in our future examples, which is very potentially likely, remind me to square it. And don't forget yourself. Square that thing. Square G prime. I think this kind of makes sense. And you can prove this by taking a first order Taylor expansion. It only concerns the first derivative, so it has something to do with the first order Taylor expansion. There is something that happens if this was 0, right here, you can move to the second order delta method. It will muck up the normality of everything. So that's just a hint for the future. It's not going to be a normal distribution, it's going to be something else. Does anybody know what it is? Very good, chi-squared. So you read the book. So it's kind of fun to read. Okay. That makes my heart warm. So, okay, let's go through the preliminaries. So that's what the delta method says, and we're just going to walk through this proof to understand the mechanics and have a discussion about it. I don't think anything's overly technically difficult, but I promise you, I'm either going to ask you about this one on some future midterm or the CLT. It's going to be one of those, and I'm going to see how you handle the remainder. Okay, today I'm not going to say too much about the remainder. We'll just make some basic statements. I will say, asymptotically, this converges at the exact same rate as that does. But that doesn't mean that this is as good of an approximation as that is. And that's because the constants can change out in front of everything. So this is ON to the 1/2, but there's a constant out in front of it. So it really depends on what the function is that we're applying this to, how wiggly it really is, so on and so forth. Okay. Good enough, Brendan? A little bit of motivation, we know where we're going. Good idea. Okay, preliminaries. Okay, recall. For smooth functions, G, usually I just put a dot in there if I don't want to define anything about what I put in there, but you can insert whatever you that goes into that function. So for smooth function g, I could write something like this down. G of x is equal to g alpha, some centering parameter, plus g prime alpha. This is going to be x minus alpha. So I'm going to just stop right there and get rid of this equal sign and say this is approximate. And we could say something about the remainder to this. So I'm going to call this thing our approximation. I think the book uses this, TRX. So that's our approximation. And the remainder is just the difference between the actual function and our approximate function. It's just going to be g of x minus TR. I'm just going to call it t of x. We don't need the r in there. And we could say some things about this remainder, that we know that this remainder should go to 0 faster than this term explodes. If you don't like the way I said that, I mean the exact same thing that I wrote down last time, that you can take the ratio of this and take a limit. In your calculus class, they probably took a limit around the center of everything and saw where it didn't explode. The remainder didn't explode faster than the approximation. And the limit that we took for the central limit theorem was in terms of n. So we didn't check exactly the radius of convergence because we didn't have to. It was always going to converge. So it's along the whole real number line that everything converged. So that's nice. Normal distributions, they have the same property wherever you are on the number line, so I can slide them all around the real number line and you get exactly the same properties. And so usually we say something about uniformity. So we'll be saying some stuff about uniformity later in this class. It uniformly works when it works uniformly across the whole number line. So we know that stuff. Here's a generalization that the book writes. So now we're going to apply this thing to random variables. I'm not going to test you on multivariate versions of this, but let's just outline what the book talks about. So consider the random variable t. And I'm going to make this multi-dimensional. This is going to be k-dimensional. T1, T2, all the way to Tk. So multivariate random variable. If you want to think about this as a multivariate normal, that would probably be the most sensible thing to think about right now. Is an example. If we were trying to be really abstract, we could say infinity. But I like to just think about normal stuff while I'm doing this. Implant an example. So, and this is going to have means. Theta. I'll give this the same sort of notation. Theta 1, theta 2, up to theta k. I don't know if this is the first time I've written this down on the board. That's my cap theta. I think it looks like cap theta, but sometimes people are like, what's that circle with an H in the middle of it? And we'll be using this a lot when we move into hypothesis testing. That's chapter 8 stuff. So that's just my capital theta. Okay. We can apply a similar approximation. So I'll show you what the multivariate Taylor expansion looks like, at least the linear expansion. I don't think this is in your calculus book, but if you understand the one-dimensional thing, I think this isn't too far of a stretch. So, by the way, if I were going to Taylor expand some function, so I'm going to just write down g of t, and I'm going to Taylor expand this, where do I want to center everything? So I'm going to write this down as approximately g of something plus something else, the first derivative terms. But I need to plug something in right here to center it, just like any Taylor expansion. Where would you center this expansion? It's not a trick question. Maybe it is. You guys are sleeping today. Okay. The obvious answer. In the bulk of the distribution. Theta. So, you can already guess that the delta method, if we do this, is going to fail miserably if the mean doesn't have the bulk of the mass of everything in there. So if it was like a bimodal distribution. Keep in mind, this all applies to normal stuff, so the mean is a good approximator for a normal distribution. I'm going to try again, over and over again, to wean you off of the mean. But if we're dealing with stuff that's normally distributed, the mean is a good estimator. So keep in mind, for a normal distribution, the mean, the median, and the mode are all mean. They're all the same numbers. So that's good. In a lot of cases, that doesn't happen. You have to be a little bit more judicious in your choices. So then I'm going to take a sum. This is going to go from, I goes from 1 to k, g prime, theta. I don't need to divide by 1 factorial here. So this is just the first derivative. So ti minus theta I. So this is just a linear term. So this is my linear expansion. I don't know if you guys know this, but it kind of looks exactly like the one-dimensional case. It kind of looks like the thing that you would do. I should be a little bit more careful and use some notation that says this is the ith partial. So I didn't write it down right the first time. So you need the ith partial derivative. Let me change the notation again. I don't really love that. I prime. I think that's what I want to write down. So when I put the I up there, it looks like I'm taking different derivatives. So I'm just working with the first order approximation. So, and this is the ith partial derivative. So gi theta right here is just g dt by gt right here, and then I'm going to evaluate this thing. If t1 is equal to theta 1, t2 is equal to theta 2, so on and so forth, tk is equal to theta. Okay, so I take that partial derivative, and then I evaluated all the thetas, and that's what's being represented right there. And I'm going to do that I times take all of those partials and plug in those values. So check. So let's check something out. This might be a good approximation, maybe. So note, expectation of gt is going to be approximately the expectation of, I'm just going to plug this thing in, g theta plus these linear terms, gi prime theta ti minus theta I. So I just applied my approximation directly. I goes from 1 to k. So same thing. So once I take this expectation right here, these ti's turn into theta i's, because we know what that is. And I can just slide this expectation right over everything because it's a linear equation. So no problem. So this is going to be G theta plus sum I goes from 1 to k G I prime theta I cap theta theta I minus theta I. I have a bad habit of when I know the term's going to go to 0, I muck up everything around it. So watch me. This is all 0 right here. And that's because the expectations, we already know. That's where we centered everything. And so this is equal to G theta. And I'm just going to point out, this is the G of the expectation of the cap T in the first place. Let me ask you a quick question. Does this look familiar to you? A relationship between that expectation and a relationship between this expectation? It looks eerily similar to an identity that I know. Sorry, I just can't keep it. My head is so stuffy today. Yeah, it's kind of like Jensen's. But Jensen's is a much stronger statement. It requires convexity of G. So to be able to apply it, and it introduces a bound to everything. So this is a weaker statement than Jensen's. Let me just ask you a question. When are these things equal to each other? There's only one time, only for one class of G's. This is true in Jensen's too, when you actually get the equality term. And that is that proof that we're going to be looking at when we grade your homework to see if you clarify that case of when you can remove the equality sign from everything. So when is it equal? Please. When G is linear. So for linear functions, why is that true? Because expectation is a linear function, so I can interchange linear things. So this is only equal for G linear. How close is this? We don't really know. So can't say too much more than it's approximately close. Are they equal to each other? Only in the case where everything's linear. I've seen over and over again in my career, people take things and they're inverting it. And they're like, oh, I want to invert like G of inverse of T. And they're like, isn't that the, inverse of the expectation? And it's like, no. In fact, they're probably pretty far away from each other. And that's what I'm going to do on your future simulation studies. Do something where I know a linear approximator is invariant. So if I wanted to make some statement about this, as a statistician, I think it's always important to quantify your uncertainty, your variability. Understand where it's coming from, quantify all of that. So if I thought that a statistician had one job, I think it's that. Understand what uncertainties mean, where it's coming from, and so it's a much more qualitative sort of thing that you have to think about first before you start doing that. That's probably the part that I didn't like about that narrow net conversation the most, is there is no answer to how good are these answers that we get out of narrow nets. There's no way to answer that. The data sets are totally biased. Who knows what you're getting out of everything? You can't quantify uncertainties. You ask the computer. I think Shane asked this question in seminar. Is there any way to quantify uncertainty? And I was thinking, what does it even mean? You can't even think about that, and the computer can't answer it for you. So, it's when you ask somebody, how much do you believe in that? It's a real trust factor. You have to believe that they're an expert in the field and they have enough experience to be able to tell you. So a computer will never get that right for us. Okay, that's just another little insert. Okay, so let's at least look at the variability of all of this? So we might want to look at the variability of GT. We're not going to be able to make a precise statement out of this, so I'll just put in my little squiggle symbols and hope that they mean something to you. They really don't mean a lot. You know, in the ballpark, I don't know. So, but we'll use the symbol anyway, it seems compelling. So this is going to be variability of our linear approximations. Again, you can see when it's the delta method not going to work, when it's not linear. So g theta plus I goes from 1 to k, gi cap theta ti minus theta I. Obviously that doesn't matter right there. So what is this thing? This is just the expectation of g theta plus some I goes from 1 to k, gi cap theta. This is prime, the prime where it should be, ti minus theta I minus g theta, their original function. And then I'm going to square this out. That's the definition. This is the expectation of GT right here. This is the function we're using to approximate it. Take the difference, square it. That's what variability means. So these things cancel each other. And this has something to do with the original variances of the TIs and the covariances of the TIs. And if you want to work through this, or you can't remember the formula, we just tell people, do it in a very simple case, like k is equal to 2. So let's just look at it for k is equal to 2, and not just write down what I hope you remember from your original probability class, but it's easy to forget these things. I think in the book, they just jump the gun, write that thing down and tell you what it is. So let's fill in this. So, expectation. Let's look at this case. Case k is equal to 2. This is going to be g1 prime theta t1 minus theta 1 plus g2 prime cap theta t2 minus theta 2 squared. I think I got all those braces right. So just expand everything. Expectation. This is going to be g1 prime theta squared. T1 minus theta 1 squared. I'll do the other quadratic term. G2 prime theta. T2 minus theta 2 plus the mixed term. G1 prime theta. G2 prime theta. Cap theta. T1 minus theta. Oh, there's a 2 in here. Theta 1, T2 minus theta 2. So expanded everything, and now I can just slide my expectation right over everything. I'm not going to fill in the full details of the next step. These, of course, slide right out of the expectations. I can break the expectation up into 3 different terms right here. The expectation, again, is over the t's. And so I just need to be careful there. I have this to turn right here, that one's squared. Is it right? I think it's right. Okay, so this looks like G1 prime theta squared variance of T1. So the expectation of T1 minus theta 1 squared is its variability of T1 plus G2 prime theta squared variance T2 plus 2 times G1 prime theta G2 prime cap theta. And this is the covariance of T1 in T2. So the expectation of T1 minus theta 1, T2 minus theta 2 is its covariance. So we could just fill this thing in right here now and say this is I goes from 1K G I prime theta squared variance of that TI plus 2 times, and we'll make sure we don't double count right here, so we'll say I less than J. That's the typical notation. Covariance TI TJ. I never try to remember anything. I just try to remember the most simple cases, try not to remember formulas, even though this is probably remarkably simple to remember once you've done it once, but it's easy to forget, so just go back to cases if you're trying to derive formulas. So that's the variability. It doesn't really tell us a whole lot, but as a statistician, I might do something like this. It's very similar to what the delta method does. So when it plays around with everything. Okay. Questions? Oh, you're saying I don't need that too. Yeah, you do need that
You have like G1 theta, G2 theta prime. But
oh, I forgot I'm here. Okay, gotcha. Yeah. So G I prime theta, G J prime theta. Nice thing is for univariate functions, that term's gone. So I probably won't have you compute too many covariances on a test. I want you doing a ton of algebra, messing up that sort of stuff. I'm going to test you more on the concepts. Okay, great, thank you. Okay, what's next? Basically, I think we'll just hit the end of all of my preliminary statements. So what we want to do next time is show you how good these approximations are and deal with the actual remainder and everything. So in dealing with the delta method, you're going to come up with approximators that look like this. You're going to compute variances that look like this. And our next set of questions is, how good are these approximations? You can do what a numerical analyst does and analyze the remainder. But again, I think what I'm going to teach you to do is to work through it via simulation. So, because it might be hard to do all this analytically in practice. So I think we're good enough right now, unless anybody has any other questions. Okay, so glance over the proof next time. We'll do the proof. And then I think what we're going to do is jump into Bayesian methods. So I'm going to say a little bit more about Bayes. I'm going to work through an actual example and not just talk about it generally, which will probably be helpful. We'll do some calculations. It's going to concern binomials and betas. I'm going to introduce you to the conjugate prior. And that's all we're going to touch and treat in this class. It's conjugate analyses. But if you guys have other questions, I do know how to do things in non-conjugate cases. So you can ask all those questions, but I'm not going to test you on it in this class. And then we're going to be switching gears and jumping into chapter 6. And chapter 6 is fun. I like talking about it, but it's not just a whole bunch of like calculus problems. They're concepts, they're principles. And I think that people have a hard time with that. So I would really encourage you to read through the sufficiency principle. Read through it, read through the proof of the sufficiency principle, please read through it. I remember sitting there reading through it in graduate school and going, I understand every line of this, but I don't get it. It doesn't make any sense to me. And I asked my buddy, Chong Tu, who's my office mate, third-year graduate student. I was a poor first-year graduate student. I'm like, Chong, man, I don't get it. So why is this the definition of a sufficient statistic? The definition of a sufficient statistic we might characterize has all the information about the unknown parameters. That's a nice, gentle explanation, but then there's a mathematical explanation that they present you with. And see if you can understand it. Chong said, Scotland, it's obvious. And he did the same thing that you've heard this joke a million times, but it happened, sat there for 2 or 3 hours, and don't bother me, I'm thinking about it. And then he came back and said, oh, now it's obvious. So I don't know if it's super obvious. I'm going to try to make it obvious for you. So I'm going to give you kind of an intuitive definition of it, but I think you'll understand it a lot better if you try to read through it. So next time, Bayes. We'll take a couple days, or not next time. We'll finish this with an actual proof and treatment of the remainder term, show how good this is, and come up with the asymptotic normality statements. Roadmap. Finish. Delta. This is a departure from the book, Bayes. And I'm going to give you a simple example, the binomial beta example, just to get us started. So nothing too extreme, but there's a lot to say. So we'll take a day or two to cover that, and then chapter 6. There is a lot of nuance in chapter 6. We're not going to cover every little bit of it. So my videos are there from the last couple of years if you want to see what I think is important. But I think people do have a hard time with this chapter because there's so much technicality and so many words. You know, it's like, just give me some equations and I want to solve some problems. But these are principles, they're guiding lights. There's one principle in particular called the likelihood principle. Does anybody know what it says? Has anybody ever heard anybody talk about the likelihood principle? They were probably yelling. People fight over it all the time. So I'm going to do my very best not to lose my temper when I'm talking about the likelihood principle, but that's usually how that conversation kind of unfolds. So I will tell you what it says. I'm going to give you the likelihood principle practical, and then I'm going to tell you why in a lot of problems you can't really apply the likelihood principle. It's kind of a fiction, but it's an idea, and I kind of like it, and it depends on which day it is. So I do want to talk about it a little bit, but look over, if you want to get started, the sufficiency principle. This is going to be a little bit new that I'm going to insert, but in chapter 7 they go through all of this. And I don't think they do it quite in the right order. They start talking about Bayes optimality and Bayes estimators before they even tell you really what Bayes is. So I'm going to try to insert that a little bit early, so if you think we're getting behind, we're actually making up time in chapter 7. So this will help us out a ton. So in chapter 7, we're going to have all these different methods, Bayesian methods, asymptotic methods, computational methods like the bootstrap, and we'll be comparing those methods. We might ask a question every once in a while like, does this violate the likelihood principle, and do we care? I have tried to test on that before. It is a total disaster, and I will not do that. So I don't want to make it contentious, but I want to make you aware of things that statisticians do talk about. There are new homework problems online, so get started on those. They'll be due, I think I posted the date on the 24th, which is not this Friday, but next Friday. So we'll aim for a review session next Tuesday. Okay, that's it for that, guys. Thanks so much. Try to start giving you a couple of those minutes back that I take from you every single time. Welcome back, everybody. We're going to go through the delta method again today. Let's just recap where we were last time. So the book kind of generalizes in the very beginning of this and talks about the multivariate case, and they never really go into it. I thought I'd just keep us on track with what the book is saying. So we'll just show what we showed last time. I think it was basically this. So if I've got a transformation of some multivariate random variable, where the t itself is just t1 alpha tk. This thing was approximately equal to g theta, where the cap theta are the means corresponding to the t's. That's what we call cap theta. So, kind of looks like Jensen's, it's not Jensen's. So, it's some relationship, you could just plug in. Basically, you're just interchanging the expectation, the order of things. So, this came from the first order Taylor expansion. So, and then we showed something like this. Variance of G cap T. This was equal to the sum. I goes from 1 to k, G prime I, evaluated at theta. There's more to write right here. There's another term I'm going to add in right here. This is the derivative, d dt I G. And I'll say this is cap T right in here, and then we evaluate the T's at all the theta positions. And I put some long little list right here. I'm going to write it just a little bit differently. I'm going to write that the Ti's are equal to the theta I's, and instead of enumerating all of them, I like to just add some subscript notation right here. So I goes from 1 to k. Usually I'll just put a bar right there. So these are the partial derivatives. So I partial. Keep in mind, when I defined this last time on the board, I forgot to put the prime right there. I think you all probably saw it in your notes. You can go back and correct that. This is times the variance of the TI's plus the 2 times covariance terms. I less than or equal to j. If you want to not impose that ordering right here, you just get rid of the 2 and double count everything. It's just a faster way to do things. Gi prime evaluated at theta, g prime j evaluated at cap theta, and then these are the covariances. Let's make those capitals. Ti, Tj. So that's what we wrote down last time. The book takes us through. Yes. I told you I'd do that. It's not an accident. I like it, or it's not intentional. It's a total accident. I do it every single time for some reason. But you swear. Yeah, definitely. I'm glad you're here. Okay, so that's what we wrote down last time. Basically, this is we can more generally state the delta method for multivariate random variables. The book doesn't go through the proof of it, but if you are dealing with multivariate cases, you would have all of these covariance terms in there. You can kind of just do that mental interpolation about what we're about to prove to the multivariate case. Okay. So let's write down what the delta method says. So formally, the delta method says for a sequence of random variables that has this property, I'll just write this down, sequence of random variables yn minus theta, where that's the expectation of yn, divided by, I'll write it this way, times square root of n. This is going to converge to a normal 0 sigma squared times g prime theta squared. Oops, nope, I'm jumping the gun. Too many things in my mind at once. So basically it says that this random variable right here is normally distributed. So for a sequence of random variables that has this property, aka it's asymptotically normally distributed, then g yn minus g theta times root n converges to a normal 0 g prime theta squared sigma squared. And the sigma squared is obviously the variance of the ligands. So I should say these are really just the variance of the actual elements that make up this thing. So if you're thinking of yn as x bar, what I mean is sigma squared is the variance of the xi's, not the variance of x bar. So they're only different by a factor of n, but I've already pulled this n over here. So practically speaking, this is how you use the delta method. I'll show you that in a second. This statement that we wrote down before is very similar to it. So if it's univariate, k is equal to 1, there's no covariance term, so that's all removed. And this is that term right here. So for k is equal to 1. So you can expand everything into the multivariate case by plugging all these things in if you're dealing with something multidimensional. So this is the statement of the delta method. We'll try to prove this. Let me just say more practically, we can write this down a little bit differently. This is how people use everything. Get rid of this. Practically, we use this like this. So if I wanted to know what's the distribution of GYN, I might say that this is distributed normally with mean G theta, and it's going to have variance G prime theta squared, sigma squared divided by n. And so I'm just pulling this n over here. So you would plug everything in and use it just like this. This is not a true statement. This is almost true. So this is approximately true. So I would compute everything and I'd plug everything in right here. Let's say you didn't know sigma squared. What do you think you would do if you were to apply this all in practice? If somebody said, hey, I want to estimate this thing, I'm interested in my uncertainty, I don't actually know sigma squared, but I want to use this result. I've got to do something really quick. What would you do to estimate sigma squared? Probably just plug in some estimator for it. So in practice, you might do something like this and plug in the sigma squared hat. So where you maybe do something like this, if you're dealing with yi's minus y bar squared divided by n, or n minus 1, or whatever your fancy is, n minus 2, n plus 1. So we'll have that discussion when we get into chapter 7. So I kind of like this one. There is a better one out there. So, but if we're quibbling about that, it's probably because n isn't big enough. Okay. So we do something like that and just plug everything in. Everything. Does everybody see how this n is floating back and forth? So if I were to get rid of it, if I did this right here, wrote the 1 over root n over there, if I were to multiply this into whatever this random variable is I'm trying to denote, this n would get soaked up over here. This would be square root of n squared. So that would be that n there. But we can't actually make a mathematical proof out of this statement because we're taking a limit with respect to n and saying it converges to something and it can't contain n over on the right-hand side. So we don't write it that way. In practice, we use it that way though. So because for any actual problem you're going to be solving, you're going to have finite n. If you do happen to have infinite n, come and see me. So I'd like to see how that works. Okay. So let's roll through this proof. Let's do an almost direct proof first and get the general gist of all of this. And then we'll fix the proof. When somebody says something is almost true, what do they mean? It's not true. So when somebody says they're going to use the pseudo-estimator or something like that, what do they mean? It's not the estimator. So how good is it? I don't know. So it's hard to say. Almost right. So let's just do our Taylor expansion. So GYN. We're just going to rewrite this using the Taylor expansion. Sum. I'll write it out like this. G theta plus G prime theta. There's no index down here on everything, so hopefully you can remember the old notation that we're using. That's just the derivative. So last time when we were dealing with the delta method or the central limit theorem, I did something like that. I'll just put it right there. Yn minus theta plus some remainder term. K goes from 2 to infinity. G, and I'm going to use our old notation, raised to the cap k, that's the kth derivative, evaluated at theta, divided by k factorial. Yn minus theta raised to the k power. And this is the remainder. So I did use the fact that I've got all of my derivatives to do this, but we really only need one more term in the derivative to really analyze all of this. So I might say something like for g, 2 times differentiable. We can do this analysis. We don't need all of the moments, but I'm going to just write them down and assume that I have all of the moments. I said moment, I mean derivatives. So I'm also conflating the language I used last time. So I will ask you to prove one of these things, the central limit there or the delta method, so try not to miss them. So I'll be checking for all of that. Okay, so not moments, derivatives. Okay, so that's our remainder term. We're going to be saying that this is negligible and we're going to toss it. So throughout all of this. So let's think about what happens is the limit goes to infinity. So I'm just going to write down this again. Limit n goes to infinity. As I do all of this, let's just rewrite everything. So limit n goes to infinity, gyn is equal to the limit, and I'll break this into two terms, the approximation and the remainder. G theta, nothing happens with the limit on that thing, plus G prime theta, yn minus theta. Maybe something happens here with the limit, plus limit n goes to infinity. The limits just roll over the addition sign. So sum gk theta, kth derivatives divided by k factorial yn minus theta raised to the k power real quickly. So let me ask you, let's just ignore this first part and focus on this part for a second. What happens as n goes to infinity here? Why? That is the answer, goes to 0. Why? It's not the same as last time. Remember we had the t divided by root n, and that was showing up in the polynomial terms, and we centered everything around 0. So it was a little bit different of an argument as to why that remainder was going to 0. This is the stuff I want you to be specific about. So say some reasons why the remainder goes to 0. So I'd say master's level proof, it goes to 0. You know, give me some very rough reason. PhD level proof, be more specific.
Why n goes to infinity?
What's that?
Why n goes to infinity, why n goes to infinity.
Oh, that's right. So note the limit of yn, what does that go to? Theta. So why?
Because theta is expected maybe by large number.
Law of large numbers, something like that. So I think that's a good reason. How about strong law, weak law, does it matter? Not for this class. So I don't really care. It's the strong law of large numbers. It converges to theta in the strongest sense, meaning it gets towards theta, and as it starts approaching theta, it stays within some bounds. It never jumps out even for just some like little tiny moment. It gets close and it stays close. So it's uniformly bounded around theta as n increases. So this is the law of large numbers. So law of averages. So the mean of the mean is the mean. You chew on that for a while. So the expectation of the average is the true average. They're all different expectations and averages. So that goes to that. So this is converging to this. That's going to 0. So all of that goes to 0. Same thing happens here. That's also going to 0, but it's bouncing around 0 in a particular fashion. So how does it bounce around 0? We know from this statement right here. It's normally distributed around 0. So it's converging towards 0, but we know something about the distribution of it. So this is normally distributed in the limit. So this is going to converge to a normal 0. And I didn't deal with the ends quite right in all of this. So this is going something like a sigma squared divided by n. It's not the correct proof because I still have the n over there. So I've kind of messed this up a little bit, but I would say intuitively we know this is going to a normal 0 sigma squared n. That's how we would do it in practice, but mathematically we've mucked this up because I've got the n on both sides of things. Same statement that I was making before. So that's going to something normal. You might think the same thing over here. How is this bouncing around? So it's not just 0, it's also fluttering around 0 in some fashion, but this is going to 0 much faster than that is. And so we think that it's negligible. So why is it going to 0 faster? I'm powering something up, for a power at least that's 2. And so something that's close to 0, if I square it, it's much closer to 0. And so that's negligible, and we might say it's so negligible that I just say it goes to 0. Super fast, and I can get rid of even thinking about it because it's gone to 0 much, much faster, and all the other terms are going to 0 even faster. So that's very rough proof. So I would say that's the idea of a proof. Let's get it a little bit more correct. So, and you can kind of see what's going on right here. So I'm multiplying also by this thing, so that's a scale factor. That doesn't change where we've centered everything. Where's the center of all of this? It's 0, and then I shift it over by g theta, so it's centered at g theta. Same statement that we were saying over here. So the scale factor only affects the variance, and anything I multiply by, I have to put it in there and square it out. Okay. A more correct proof. So let's just write down what we said. So we know yn minus theta goes to 0 in the limit I can either write that here or write it out here. Both are common. They mean exactly the same thing. I could probably even get rid of the limit symbol because my arrows mean limit. So that's the typical notation. And yn minus theta raised to the k for k greater or equal to 2 goes to 0 much faster. Then that thing goes to 0. So, in that sense, we think we can just exclude that. In terms of an asymptotic statement, how fast things are going to 0, we only care about this one because this is the one that's going to 0 slower. And so we exclude that because the asymptotics of this are negligible compared to that. So we just toss it and get rid of everything. Of course it matters, how fast those things are going to 0, and how fast they're going to 0 has everything to do with what g was in the first place. So that affects the constants in front of everything. So different g's will have different constants, and the much faster will be relative to that. So, okay. So here's a more correct proof. To do something similar. Yeah, don't want to get into that. Just write it here. Okay, I'm going to write down g is before limit n goes to infinity. G. Let me write it like this. I'm going to write down exactly the same line, and then I'm going to change it just a little bit. G prime theta yn minus theta plus this remainder term. Myself a little different. K goes from 2 to infinity. G, K partial evaluated in theta divided by K factorial yn minus theta to the K. So same line that I wrote down before. The limit, I should write this over here, the limit n goes to infinity. I'm going to include the sigma over root n in all of this. So I'm just going to vary my sigma root n into all of this. So this is going to be divided by sigma over root n, sigma over root n. So that I at least get the root n's in there. I don't really care about the g theta. I can just float this back and forth on the left or right hand side. The limit's not really changing anything with the g theta term. So I'm not going to think about it right now. But I can think about this term right here. And I know how that's convergent. And if you understood that statement about the central limit theorem and everything you've been doing since your first semester of statistics, you know how that's distributed. So we've already made a statement about it. We didn't write it down precisely the same way we're going to treat it here, because we have things shuffled around. We have the theta over here. But that's just a shift parameter. So this thing right here is normally distributed. Somebody help me out. Which normal is this? Center at 0. Variance 1. So that's the normal 0, 1 statement. So you can just divide by that scale parameter, kick this root n right up here. It's about the same statement right there. I just put the sigma in there a little bit differently. If I move it to the right-hand side, vary it into the normal statement, I have to square that out and it becomes the variance. So this term right here, what's this doing? I don't exactly know the distribution of all of these things, but again, I know that they're negligible compared to what's happening over here. This is dominating everything. So this is converging to 0 real quickly. So this is going to 0. That's than this thing. So this is going to 0, it's bouncing around 0, but we want to deal with the uncertainty in it. And all of the uncertainty around this is negligible compared to that. So there is error there, something there. So, but we don't care about it, we're just going to soak it up into the approximation. So that's normal 0, 1. So now I've dealt with the n appropriately. So now I got this scale term right here. So this whole thing right here is going to a normal 0 g prime theta squared. And I would consider this proof. So just telling me why this thing is negligible. I have the sigma over here, right here, so I haven't written it out exactly the same. So you could butter it up and make it look exactly like this statement just by dealing with sigma on the right-hand side of everything. So, but I think it's exactly the same statement. Any questions about that? So that's my version of the proof. So I would give that 101% credit. Cool. Proofs are funny. So everybody's got their standard for what's a correct proof. So, and I've played this game for a long time, where it's like, you want a more correct proof. So what I love is when people are able to prove things that aren't true. So those are the proofs that I really dislike. So make sure it's true and you understand it before you start proving something. That's what I learned as a math major a long time ago. Brendan.
So I have a quick question. So I'm thinking about the summation term, and like obviously you could expand that out like squared, cubed, and so on. And so how do you know? I get that y goes to 0 faster than the other one, but how do you know that starting at the squared term is when you can say, like, okay, now it's basically to 0?
It's anything that's asymptotically bigger than this term.
Okay.
So because this is dominating the asymptotics of it. So it could be the like, not even the squared term, but the 1.5 term.
Mm-hmm.
So it's going to 0 faster. So what's controlling the asymptotics? The lowest order term. Does that make sense?
Yeah, I think that
Are you sort of asking like why arbitrarily choose the first term, why not the second term?
It's a good question.
yeah, it's like basically why do you
There's
stop
a-
at the first?
There's another question we could ask that can't we just make this a better approximation by expanding into the second order term? So great question. So let's answer that. So it's appealing to think about it. Let me just get rid of this stuff. I thought about that. So if you're gonna do all this, just take it to like 7. You know, it's not like it's harder to do. Great question. There is a reason. So question, why only use a first order approximation and not a 7th order approx? I'll just write the second order. So let's just stare at this. So if we did use the second order approximation, our remainder would start at k is equal to 3. Can anybody answer the question? Let's just write it out. So if I did something like this, g theta plus g prime theta yn minus theta plus g double prime theta divided by 2 factorial yn minus theta 2 plus remainder. We know all that stuff's going to 0, and you're right, this would be a better approximation to everything. So how is that distributed in the limit? It's like normal. So it's some, I haven't dealt with the ends right, but it's approximately normal, and we might use it as a normal. How is this term distributed? Chi-squared. What happens when you add a chi-squared and a normal to each other? Because that's how this would be distributed. So our approximation would have a normal distribution, an error that's normally distributed, plus a chi-squared distribution. It would be something that's rescaled. So rescaled chi-squared. So what is a normal plus a chi-squared? Does anybody know? I don't know either. So that's the reason. So because you don't know what distribution that is easily. Could somebody have figured this out? What's a normal plus a chi-squared distribution? And tabled all of that stuff? I guess, but it's not an easy distribution to work with. You've got to think back in the 60s, you know, they were pretty limited in all of this stuff. You could only table so much stuff, and I'm going to assume that distribution is relatively complicated. So in a simulation study, you can work with it real easily. So not have to know exactly what is the analytical form. But the delta method is something you would do if you wanted to write down analytical equations. So, and you couldn't do it. So what is a normal cubed? What distribution is that? So if I went to the third order approximation, I don't know either. So I'm not sure what distribution that is. So what is a normal cubed plus a chi-squared plus a normal? I don't know. So, and you can take this argument to the 7th order approximation. So now you're dealing with some distribution that you don't know, and it might just be just as complicated as the original distribution. Is that the question? So that's has something to do with the 2nd order delta method. I think I misunderstood this when I just heard 2nd order delta method. It's just the 2nd order thing. The 2nd order delta method concerns cases when G prime is 0. So if G prime is 0, then you can't do all of this because you're going to say, I've got a normal distribution with 0 variance, which if you're trying to do the things statisticians do and quantify your uncertainty around something, 0 variance isn't very useful for doing that. So, so the 2nd order delta method is only used when that's 0 right there. Then they'll kick it into the 2nd order term, and we do know things about chi-squared distributions. So I think I've said enough about that, and we won't even cover the 2nd order delta method just because the question is so good. So it gives us the insight. I won't test you on it, but let's just kind of look at an example where that happens, where you might apply the 2nd order delta method. This example is in your book. Thank goodness, examples. So we'll get into examples. This is how this class is going to roll. We'll kind of generalize, do examples, do simulation studies. So just kind of bounce through those 3 different modalities. Sometimes we'll talk about philosophy too. So that seems to be a professor favorite, but students never seem to enjoy it quite as much. So we'll see who does. Just an example. So let's say xi's are, let me make sure I have this example right. Xi's, everything's IID. Again, my rule is if I don't write IID and I don't tell you the dependence of things, I'm implying it's IID. So let's say this is mean mu variance sigma squared. So typical sort of thing. I've got n data points. And I want to consider the transformation. Transform I'll say G, and I'll parameterize it in terms of mu, because that's what we're going to work with and operate with at the end of everything. Where are we going to center everything at mu? That's where we're going to take our derivatives. So I'm not going to transform the random variable in my statement, but I could have written that down too. So I'm really looking for G, maybe X bar. But it doesn't matter. You can think of it as a dummy argument, but this is what we're going to compute on. So we're just going to take the quadratic transform. So the delta method. So what I'm going to do to compute all of this is I'm going to say G X bar, and this is going to be approximately. So we'll apply this in more of an engineering sense. We're going to do something with all of this. I'm going to say this is going to be normally distributed, centered at G mu, and then it's going to have this corresponding variance. G prime mu squared times the variance. Which variance do I plug in right here? The xi's or the x bar? the X bar is here because I plugged that thing in here. So you gotta be careful on this. You know, it's like, which random variable are we talking about? So this is the sigma squared over n one. So this is gonna be X bar. In that statement over there, the n is pulled over to the left-hand side. So lots of people get confused on this in the upcoming homework. The way you use it is the one on the test statistic that you're actually calculating. So variance of X bar, we know that part. Sigma squared over n. So this right here is just going to be mu squared. And this thing right here is going to be, we could probably take this derivative in our head. G prime mu is equal to 2 mu. So this is going to look like 2 mu squared. So this whole thing is normally distributed mu squared 4 mu squared sigma squared over n. Get rid of some of that stuff. So that's what the delta method says. So you do something with this. Again, this isn't inferential yet. So if I were going to try to estimate all of this stuff and say something about it, what I would probably do is plug in X bar for all of my mu's. That's how you would use this in practice. So let me just make a statement about this. So in practice, to be useful, this is just a probabilistic statement right here. But inferentially, to use all of this, we need to estimate mu. So estimate mu. Throw a hat on top of my thing to say that I'm estimating. And most reasonable people, if they didn't know anything about any of this, they would use X bar and just plug that thing in. So the mean. And they would use normal X bar squared for X bar squared times sigma squared over n. You might wonder technically what did we do, and we'll talk about this maybe when we get to chapter 8. This is called pivoting. So maybe you've been introduced to that when you're just substituting all of this stuff. I'll be more formal about what a pivot is later in the class, or pivoting. So we just use that as our estimator. So if somebody wanted to understand the uncertainty of all of this stuff, maybe it's normally distributed X bar squared, 4 times X bar squared sigma squared over n. If you didn't know the sigma squared, you'd estimate that as well. So I'll just throw in a hat right here. So you would know how to estimate that sigma squared. You'd use the original xi's to do it. If you just computed X bar, you would have no hope of computing that. You would need to know the sigma squared. Okay. As mu goes to 0, this thing goes towards 0. This goes to 0 right here, and that thing goes to 0 as well. And so that's pretty unuseful. So that says that the delta method approximation, if mu was 0, we're tending towards it, then I would say, oh, my answer is normally distributed, centered at 0, variance 0. So I think the answer is 0, which is totally unuseful. So I don't think it's 0 as well. What are you thinking the actual thing is? So remember, this thing is just X bar squared. So we know a little bit more about this test statistic. So in reality, we could actually write down exactly how this is distributed has something to do with the chi-squared. It's a scaled chi-squared. So x bar n squared is really a chi-squared with 1 degree of freedom right in here, and it's multiplied by sigma squared over n. That's the book. So that's a chi-squared distribution. Normal squared has something to do with a chi-squared. If you ever heard of a non-central chi-squared, you can probably figure out what it is. It has a shift to it. So they make you play around with that in regression class a lot. Maybe something like that. I remember that from grad school where it's like, oh, I've got to remember all these different forms of chi-squareds. So that does go away after a while. I haven't touched them since. Okay, so this is a terrible approximation. So if G prime of whatever your estimator is, so I'm speaking a little bit more generally, just about general theta again, if this thing is equal to 0, the delta method doesn't work. So what do? You go to the second order term. The second order delta method says something about a chi-squared distribution. I'm not going to test you on that. I'm not going to ask you to know exactly what that chi-squared distribution is. I just want you to be aware of the concept. So note, maybe use the second order delta method. And this thing has some chi-squared distribution. I'll just write down a scaled chi-squared disk. That's kind of cool. I can imagine back in the 1960s, this was all very neat, where it's like, oh, I could actually write something down and use something and do something with it. In an approximate universe that we live in, this could have been useful. So my maybe is, I really don't love the performance of all of it. So let me just ask you the question, when does the delta method not work very well? When would you expect for it not to work very well? What does that mean? It means that it gives you errors that are too big to be useful in your case. So I can think of a couple of different reasons why this would happen. Could you guys give me one?
It probably doesn't work well when your sample size is small because everything's built on asymptotics.
That's true. So that's true. If this statement isn't quite true yet, there's a fundamental breakdown in everything. So when the normality isn't there. So when n is small. That's true for all asymptotic methods. So, any others? When what? When G is not very smooth. Yeah, exactly. G not very smooth. I'm going to say the linear, so not smooth. I guess that would subsume what I'm thinking about, that the linear approximation isn't very good in the first place. So I think those are two good enough reasons. So we're gonna give you something to play around with. Let's come back to an example next time that I'll be asking you to code up. It's also in the book, and they actually do a full-blown simulation study in chapter 10 on all of this. So that's the chapter on asymptotics that we're not gonna discuss, but I kind of like that chapter because it's pretty mathy, but at the end of the day, they do all simulation studies in there. So we're going to be doing a little bit of chapter 10 while we're still in chapter 5 and just doing all the comparison. So we'll come back next time, look at another example, and then we'll jump into Bayesian methods, how a Bayesian might approach the same problem. Okay, that's it for now, guys. Thanks so much.